Good evening, and thanks for joining tonight's TI Technology webinar hosted by Texas Instruments, where tonight we're going to take a look at making mathematical connections across a vertical curriculum. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI technology to make tough-to-teach, tough-to-learn concepts accessible to all my students. Tonight I'm excited to be joined by our two panelists, Lynn Adsit and Kim Shelderup. Lynn is in her 40th year of teaching high school mathematics, who continues to use technology as a tool to explore and understand mathematics. Lynn currently teaches AP Statistics, along with honors pre-calculus, and using TI-Nspire and TI-Nspire Navigator technology at Mercer Island High School. Lynn also enjoys her role as an instructional coach. She hosts a monthly TI user group meeting where she explores ways that technology can enhance and deepen student understanding. Lynn, thanks so much for joining us tonight. And Kim is in her 26th year of teaching mathematics, integrating TI technology to enhance the understanding of mathematics and to build conceptual and procedural fluency with her students. She's a national board certified teacher, department chair, and AP Calculus reader. Kim has presented at regional, national, and international conferences. She also teaches AP Micro and Macroeconomics. Kim, thanks so much for joining us tonight.
Thank you very much. I'm excited to be here. And now Lynn's going to speak because I think I muted her.
She did, but that's okay because I'm still here.
Thanks so much. We're expecting a large crowd, so your audio is muted. Feel free at any time to ask any questions of Kim or Lynn using the Q&A window on the right side of your screen. We'll also be using the chat window to send general messages. As a reminder, the session is being recorded, and we'll provide a link to the event certificate of attendance at the conclusion of the webinar. We hope you don't have any audio issues tonight, but if you do, try selecting Communicate from the very top of the WebEx menu and choose Audio Broadcast. At this point, Lynn is going to discuss our agenda.
Thanks, Michael. Well, we're going to do welcome and introductions, as always, and then we are going to introduce what we mean by making mathematical connections across a vertical curriculum. Most of our talk is going to be around some activities to help people understand what we're talking about here. So the activities are going to be graphical analysis spanning grade levels, and then talk a little bit about why you would want to use these powerful problems. Then we'll introduce a second problem from start to finish called the garden plot problem. And then finally, we'll hopefully, if time permits, we'll talk about how to bring a powerful problem process back to your school. And then finally, don't forget to stick around for the webinar drawing after we're finished, because you might win something.
Thanks so much, Lynn. And Kim is going to discuss our expected outcomes.
Well, welcome everyone to the beautiful Northwest. I see that we have some waving us hello from Texas and Pennsylvania and a variety of places around the U.S. So welcome. Oh, there's an Indiana. Have fun. So we're going to explore some activities that highlight essential concepts and making connections. We're going to look at technology and how that can support your students' understanding. And we will then share how you can implement and bring this strategy back to your school and your colleagues. So I hope you have a great evening. Hello from New York. Hello from, oh, that sounds like a TV show, isn't it? Live from New York, and here we are.
Live Seattle.
Thanks so much, Kim. You have control, so feel free to share your screen.
All right.
Great. Thanks, Michael.
Thanks, Michael. At the beginning. Uh-oh. So we need to, sorry, we were playing. All right. There we go.
There we go.
Playing and forgot to restart. Right. So welcome to Powerful Problems, Making Connections Across a Vertical Curriculum. And it's really exciting to have everyone with us today.
So first thing, in our mind, we were talking about what does that mean to connect mathematical ideas across a curriculum, and we were thinking that has to do with a thing called a powerful problem in our mind. So a classic or common problem that kids see over and over again. We hope that that problem is rich with mathematical connections and using the same scenario at different levels. So kids will see this and say, oh, we did this last year, and then we take it and go even deeper. So the concepts and processes are built upon and deepened at each level.
And it's one piece when I think very quickly is I so appreciate my colleagues using this process in our building, because when we get to optimization, which tends to be a challenging concept in the AP exam with kids, our students, they're like, oh, we can do this, because they've seen it throughout their high school math experiences. So we're going to start with graphical analysis.
So the graphs that we're going to be using in this setting are AP Calculus release exam pictures. And what you should find in your participation or participant resources, you should find the graphs that we're going to talk about in PowerPoint, along with some others that we thought might be interesting. These are just to get you started, and then obviously you can create your own, maybe to get at other questions that you think would be good to draw out from your kids.
So we've organized these with a variety of questions with different levels. So these levels could be Algebra 1, could be a pre-algebra, could be an integrated 1, and using the graphs, because graphical analysis is important for students to understand and be able to do. So we just threw up 4 questions here. One is determining G of 3. Students have learned their function notation. Although I just realized this picture is a graph of F because we changed it from G that we started with. So we really should say determine F of 3. I do apologize, I just caught that. Finding an area of a triangle. One that's challenging for kids is where the graph equals 1. So now we're asking them to find those X values, and they tend to say, yay, I found 1, and then miss the fact that there are actually 3. Writing equations of lines, we want students to be able to do that. What are some other questions that you could think of that you could ask your students?
About this particular graph in a level 1, algebra 1, pre-algebra type course. So go ahead and add a few in the comments section, and maybe we'll try to see if we see any. So what is the rate of change between 2 points from Jenny Kelly? Or Janine, I'm sorry. I think I said that.
Great question, Janine. So asking a different kind of question for their slope and using a good language.
So Connie is suggesting increasing and decreasing, and where's a maximum and a minimum, and maybe introducing that vocabulary to kids at that level. What are the zeros of the function, and having a little discussion about that. So yeah, so those are some really great ones. And we thought about, I see someone saying, where's the graph steeper or less steep? Where does it have a positive or negative slope? Or how about restricted domains, things like that. So there's a whole lot of things that, given just a very simple graph that kids would see at the calculus level, that we can have kids starting to think about things on that.
Another piece that I think is nice that sometimes students struggle with is we talk a lot about X's being positive and negative, but we don't necessarily really focus a lot on where is F of X positive or where is F of X negative. Again, another way to bring out that function notation and talk about positive and negative above the X axis or below the X axis.
Mm-hmm. Okay, so we're going to move on to level 2.
Okay, so level 2.
Level 2 is basically we think of it more at a geometry level. So trying to think of what are those things that kids in geometry are working with, where they might revisit Algebra 1 type questions, but also using them in more of a geometry area. So some things we're thinking about is finding areas and perimeters of particular figures, talking about distance and length, translations, things like that are some of the curriculums. So the image we have this time, we found one that had a semicircle in it, and we figured finding areas of circles or perimeters of circles and things like that would also tie in with the geometry. So a couple things that kids would be doing at a geometry level might be finding the length and slope of the segment AB, reviewing finding slope, but also using distance formula at this level. Determine the area of the semicircle. Reflecting F over the y-axis, being that kids start doing transformations at that level. Kim, what are some things you're thinking of?
And another one is when you get into the quadrilaterals and give them 3 points, and then they have to find a 4th point, F, to make a parallelogram with points C, D, and E. The most common one, of course, the students will find is in the 4th quadrant, but to ask them to expand and find 3 different locations for this point F to make a parallelogram, and then that kind of extends that simplistic case in the 4th quadrant, where they have to think outside the box and be a little more creative in their thinking.
So some other things that kids could be asked to do is to find the areas of the function sandwiched between the function itself and the x-axis. And so here they might be adding the areas of the triangles and the semicircle. And boy, we get some shading of intervals without kids knowing that they're starting to think about making those areas to the x-axis.
So what are some questions that you can come up with?
Total distance of the segment.
Great question.
From A through E, yeah.
Yep.
Try to get some names with that.
I know, but they flash up fast. We're trying to give credit where credit's due to your name.
Yeah.
Do you have some more ideas?
So I'll throw some out while people are thinking. Another one that kids do a lot in geometry is the whole idea of transformations and translations. And so saying what would the function look like or the graph look like if you were to translate it up 1? What would be those translated points? So draw a picture of it. What do you notice about the segment lengths of AB and the translated segment A prime, B prime? And, comparing some of those, drawing out the fact that they're going to come out the same.
And getting students accustomed to drawing, writing new functions in terms of an old function as a part of their describing their translations.
Dilations as well. Yeah, that's a big one that is kind of real unique to the geometry curriculum. So having kids have the ability to do that.
And thinking about conjectures. So if the graph is translated, can they make a conjecture about the slopes or the lengths of the segments after a translation?
So another one that was just suggested was, what kind of shape would you get if you were to rotate the segment AB around the x-axis? So now you can kind of get into that 3-dimensional conic shape and maybe even talk a little bit about what might be the volume of that, which could be a really cool question. Rate of change of specific points, that's Corey Bennett. That's great too, and maybe even tying that into doing some things with, if you have the segment AB, asking the kids to create a parallelogram with 3 other segments. How could you draw one, and what would be the area? And there's a whole lot of things that you can do with that one. All right, let's move on to level 3.
Yep. Okay, level 3. So at this point, we're kind of looking at more of the Algebra 2 level. Students have had some experience with quadratics, But now maybe it's an interesting piece. We'll now write an equation for this parabola. So that piece of this curve that's the parabola. Then they could write a whole piecewise function for the, oh, see, this is our F and G backwards. I think we flip-flopped the graphs and then forgot to fix it. So we do apologize. Sorry about that.
That's not right, but.
And then getting back to, remember in the Algebra 1, a participant was talking about average rates of change. So again, bringing in this idea of average rates of change by saying, what interval do you have the largest average rate of change? So they have to kind of test a variety of places and decide where that might occur.
One other one that's on there is writing a piecewise. I saw somebody suggested that at the level 1, which is great, but now at this level, same thing again, but now we add that quadratic into the piecewise function, which could be really interesting. Some other things that possibly could happen at this level would be to find
inverse relations.
Mm-hmm.
What would the graph look like if we were going to find an inverse relation for the graph? Or somewhere we're getting some nice ideas.
Mm-hmm. They were just having a comment about some of the curriculum in New York State, New York City. It went by too fast, I couldn't tell. But so other things that can happen at level 3 would be looking again at translation, but looking at translating the entire function, perhaps using some dilations or scaling as well, reflecting over the y-axis, reflecting over the x-axis, having a beginning discussion on would this function have an inverse that's a function. So,
and another piece that's nice, because we now have that parabola, is to have them to estimate the area between the x-axis and the curve for the first quadrant, and see what are different ways that they could estimate that area between the parabola and the x-axis. Count squares, approximate, again, get into say, well, what if you do rectangles, and start talking about when we have an overestimate or an underestimate, and start getting into that language that's used at the calculus level.
Right. So you can use things that kids already are experiencing, but then having an understanding of where kids are headed, you can ask them questions that they wouldn't be able to do directly, but they can do a lot of estimating, which is a really important kind of idea. One other thing that somebody was mentioning there was the whole idea of the inverse, and bringing in that language about the horizontal line test, the vertical line test, how that might play out with this particular function. Kind of rich in that way too.
There's some more.
Any other ideas before we jump to our next one?
There's lots of them. Any other ideas? No, there's something that goes fast.
Discuss slope of each part and how that would be done on a curve.
Oh, thinking about slope on the curve.
Okay, so giving them certain points and then what that might do and how that might relate to average rate of change and things like that. Okay, so we're going to go to level 4, which kind of is your math analysis pre-calculus type level. So a lot of similar things that kids are doing in the Algebra 2, but kind of taking it to that next level. And we thought this was an interesting problem or graph because it's got a circle in it. So with the circle, it allows us to kind of look at a little more complex type things. So one thing might be writing, again, the piecewise function for f, but now kids have to think about how would I write the equation for that quarter circle as a piecewise. Another possibility, we use a lot of function notation and talking about a new function in terms of an old function. And so here, first graphing it, maybe talking about what are each of the pieces of that function notation doing. Maybe have a couple different graphs and ask them to do it with different ones that aren't common. A lot of times I find with my kids, I don't know about you, Kim, but with my kids sometimes they're very good at doing it with absolute value or quadratics or functions that they're familiar with, but when they have to do these transformations with functions that are unfamiliar, they get a little nervous about that and they're not quite sure how to approach it. So creates a lot of rich discussion there.
And another one is take away the numbers and give them some generalizations. So we're saying that, for example, in this case, it's for k greater than 1. So what would happen and what are the effects of the transformations on, let's say, a particular point of the curve given a transformation in function notation? So again, sometimes I want to say, well, what number is k? And we're trying to help them generalize and look for patterns and think about patterns.
And so some thoughts you guys might have on what might be some other ways. I see something here from Katie, use geometry formulas to find the area under the curve from 2 to 5. That might be kind of fun. Yeah, in fact, that was one we were talking about just before we started here, was using that whole idea of finding the area between the curve and the x-axis. And really with that quarter circle, it's kind of an interesting problem where they have to do some finding areas of 2 different shapes and subtracting, which they probably haven't done for a little bit. So good one.
Yeah.
Another thing that my kids at the pre-calc level we do a lot of is asking them to find the tangent to a curve at a point. And so and using circles obviously to do that. And this allows you to do it. Like, what would be the equation of the line tangent to that semicircle when x is 3? So there's a whole lot of things they'd have to kind of go through to get that to happen.
It would force them to have to remember that the tangent to a circle is perpendicular to the radius and bring back some of those ideas that they may have forgotten from their prior courses.
Which kind of brings up a point that we've had a big discussion in our department here about forms of equations of lines and how important the point slope form is for kids to be able to use the point slope form, because actually that makes this problem a whole lot easier than transforming it into a y equals mx plus b. And being able to do that, they end up using that form quite a bit more when they get on to calculus.
And the students, it's been really nice because I've been teaching calculus for about 20 years. And I remember in the early years of working with the kids and writing equations of tangent lines, and how often they'd get the calculus and find their slopes, they'd have the point, and then they'd do y-intercept and make an arithmetic error. So getting them away from the y-intercept form and really into the point slope earlier rather than calculus being the place that's their go-to has really helped students not make those errors. So in our building and even down to our middle school in conversations is that the students are coming in from the middle school with point slope as their go-to equational line. They have familiarity with the others, but that's really their go-to. And it's so nice to see that as the go-to and there are less errors that the students are making.
Okay, so if you have I'm kind of trying to watch between the chatting and the pop-up thing. So maybe while we're waiting to see if there are any other questions, let's go to the.
You know, another kind of question to ask about this that's interesting is, say, something like give a function g in terms of the function f that would have the characteristic of the maximum point at 3, 7. So what would that look like? Because now the maximum point in this graph has changed. And that's a different way of asking that same transformation, but asking it from a different entry point.
So another one is, let's see, it's Dewey is suggesting maybe potentially define the graph as a position function and then start talking about velocity. Might even be kind of interesting. I don't know, I'd have to think about this a little bit, whether you could write parametric equations for what's going on as well. I don't know, or I don't know, I think that might be a little bit challenging, but those are other things that might come up in a pre-calc class. So if we can kind of go over to the TNS files.
Yeah.
So another thing that we put together for you in your participation packet is, not that you would use all of these with your kids, but there's a TNS file for the Nspire users where it's got various kinds, go back to
you control.
So going back to the same questions, but if you have an ability to have the kids answer them in a document, sometimes that draws them in a little bit more to share. If you happen to have a navigator system or such, you could collect quizzes on these values and then have a discussion at the Algebra 1 level about the answers that kids come up with, particularly where it says estimate where g of x equals 1. And if a whole bunch of kids give one value, hopefully one value but different ones, and then talk about why maybe there would be more than one, and helping kids see those kinds of things. So here's another one where they could write the equation, and then the graph on the left is actually active, and if they click over on the left-hand side here and hit tab, they could actually write in the equation and check to see if it's working for their particular graph. The grid's set up so that it should match up nicely. So throughout this whole document, a lot of the questions that we had on our PowerPoint tried to make it so that it would become a little more interactive with the kids and such, and places for them to do calculations and hopefully draw some conversation. Here's this is where determine 3 different locations of the point F to make the parallelogram. So kids could actually drop points on there and then just see whether they're getting parallelograms. But
and
anyways,
use the tools to test their slopes. And
right. Use the
geometry tools.
So anyways, this is in your participation folder as well. So hopefully, one of the nice things with having the document, if you do have Nspires, is that you can cut and paste certain pages into your own document. So you can start with some of these and then kind of take off with it if you want to do that. The Nspire document, by the way, should be in the Google Drive link folder that you guys got from Michael. So it should be in there, and then all you do is you download it. That's what Kim did. She took it right off of your packet and then downloaded it for us to use tonight. So, okay, so why do we do this? So why go through all this kind of thinking? Well, there's kind of 3 big reasons to do it. Research sort of supports it. Articulation across grade levels helps.
Yeah, the document, the TNS file is easy to alter.
Oh, very easy. That's why it's in there. You can alter it within the one you have. You can create your own document and then cut and paste those pages right into your own document. So you can make it really hit what you want it to do. And putting your own images. So once you kind of get kind of the hang of it, you could put your own calc images. By the way, the images that were in our PowerPoint are also in the Drive, but we also added a few other ones that we thought were kind of interesting but didn't have time to talk about tonight. So those might be nice ones to follow up with kids in the math. Okay, anyway, so we do there's a lot of research supporting having kids thinking deeper and melding a lot of different ideas together in one setting, articulation between people teaching the same course, a lot of good discussion, but also between courses so that you can kind of see where a kid's headed, where have they been, and have a better sense of how to build on those. And then most importantly, these hopefully help kids deepen their understanding of really important concepts, those leveraging concepts that kids need as they progress mathematics.
And it also helps students to see that the courses and everything they're learning is a progression and builds, and having something they've seen before that's familiar yet different helps them learn to make connections between problems. So it also helps us say that we know from brain theory that building new learning on old learning helps to support, makes it stick, helps support retention, that they construct a lot of their knowledge. Learning's not linear. This also, some students will find that maybe at the Algebra 1 ideas that they had, they didn't quite get, but then they got to Algebra 2 and it's a similar problem. Say, oh, I get this now, when they may not have understood it in the past. And then they feel that power of learning. Also gives hits a lot of different learning styles and developmental paces. Is that there are entry points for every student. They may not know every question, but there's always at least one question that they can answer in terms of reading their graphs.
Second thing, it fosters communication. That's that articulation idea. Helps build discussion within a course. So if you have a problem that everybody in that whole course is going to do together, then you start developing the questions. You start saying what's really important about it, what are the critical elements to draw out. So then kids are getting a common experience within a course, but also the discussions across levels help build the continuity. But also, I know I have a lot of conversations with Kim about, so I'm doing this in my pre-calc class. How should I talk about it so that whether they're ready to just jump into calculus and not being held back because I'm using poor language or I'm not really developing the concept well enough earlier. And then it helps clarify how to deepen the understanding with kids, and that discussion with peers is really a valuable thing. I mean, we do it a lot.
We do. Going back to kind of talk about the continuity is such a big discussion piece in our department. And again, fostering a lot of this communication in the department that's given consistency for the students going through at all the different levels, but continuity in particular in really having that discussion about a function's continuity versus continuity at a point. And we have had a lot of conversations with that throughout the years within our department, such that the students, when again get to calculus, and they're very clear about the difference when you're talking about a function's continuity versus continuity at a point in the function. So it's really been very powerful having these discussions and sharing similar problems that students see in a variety of levels and revisit and rediscuss. Helps the students become flexible thinkers. They're fluent users of math and math practices because that happens especially to communication and the connections, and they do see the connections over the years. It makes them much stronger mathematicians, which is our big goal.
So I'm going to jump in real quick here. And when we're spiraling the topics, I think one of the really important things is you can introduce or develop ideas at appropriate times for kids to understand them. And as the picture shows on the PowerPoint, we do a lot of work where kids are working in groups. And so giving these problems and having kids discuss them, the richness of conversations and the ability of the kids to be able to explain to each other their understanding or make it clear for kids has just been, it's really amazing. It's been really great. So, okay, so we'll move on to our next example.
As I always say, the students are successful in calculus because of what everybody else does. But for the really nice part, I get all the credit for everything the rest of the department does. I do try to give it back to them and let them know what a wonderful job they're always doing. So this is our first powerful problem that we developed within the department. and have used in the department, which is where this idea and all of it came from, where we're trying to come up with more and more topics. But this was the very first one that we're going to share with you, and this has to do with optimization. So here's our situation.
So this summer I want to make a garden in my backyard to keep out the neighborhood dogs and deer. I need to put a fence around my garden. I have enough money to buy 200 feet of fencing. I can make the width of my plot anything I want, but my goal is to get the most garden area possible with the fencing I have. The equation for the area of my garden is blank. A equals negative W squared plus 100W, where W is the width and A is the area of the. So one of the things that we tried to do from level 1 all the way through level 4 was to basically use that same entry question. That's why I've taken the time to read it. And then what happens after they read that problem at Algebra 1, we want an easy entry point for kids, low entry point, so everybody can at least get started. So we ask them to make a table of values using the area equation above. So again, they get to practice inputs and outputs. And then we ask them to plot the points on the coordinate plane, and then ask them what shape do you get. And so the kids, spend a little bit of time together graphing and making sure they can where to put their X and Y axes, and looking at the inputs there, how should they place their axes and stuff, which is kind of important. Usually it takes a lot longer than you would think to get that first part done. Then we ask, do all the points in your table give good values for the width and area? So we kind of take a look at that whole negative 10 for W, that we can start to talk about restricted domains for a real world application versus the domain for a general function that's not connected to application. So it's kind of a natural way to be able to do that. We ask the kids to think about it first, and then we ask them to explain their thinking.
We ask nice explanation about looking at the values. Where do they get the maximum area from reading the table? Can they connect that to the graph? Do they think that's the very largest possible? Think about, could there be something else? What would our area be given specific values? And could there be another place where they would get the same area? So it's coming back to that symmetry in the problem.
Yeah. So, and you'll notice here, we're already starting with this whole idea of what's going to give the maximum area idea. So kids even at this level are starting to get that whole idea of optimization.
And then we go to level 2. It's the same scenario, same equation. Now we're asking them different kinds of questions. We want to, again, find our maximum area. What kind of equation, factor, what does that do for you? Find the x-intercepts.
Okay, and I'm going to stop you there, Kim, because one of the things that we're noticing again, which hasn't happened for a while in our department, is that kids are feeling like they have to multiply everything out right away. And we're trying to get them to take a look at the equation of a quadratic from a factored form, if that makes sense. So they can then use that to do some other kinds of things later. So that's why we're having them factor, both to practice factoring, but also we're going to leverage that with the x-intercepts and the vertex in just a few moments.
And to help them really think about when they find the vertex in two different methods is to remember that the vertex is that the x-coordinate of the vertex is the average value of the x-intercepts. So that's a real powerful, because, again, as Lynn mentioned, what we see a lot of are the students taking a quadratic in factored form, expanding it so they can use negative b over 2a is the only way that they're thinking about that x-coordinate of the vertex. So trying to help them think more flexibly about the problems. So
another thing that we have the kids do, which is a little different than with the Algebra 1 kids, is once they have the equation, rather than setting up a chart of values, now we ask them to graph it using some critical attributes about the graph, like where are the x-intercepts, what's the y-intercept, where's the maximum. Can we draw a sketch of this graph without having to plot a whole bunch of points? So, kind of moving them into that next level.
And then asking what would our width be if we gave them a fixed area, and again getting them to practice working with their quadratic formula or factoring something different. So next one, again, same scenario. We have this money to buy our fencing, and now we're not giving them the equation. So they have no equation, and they're asked a variety of different questions so that they can now develop the equation themselves.
And so the first question here about drawing a diagram of the situation and label all information, kids just don't want to draw a picture. And so we start to give them situations where they have to draw the picture, label, define their variables, things like that in order to sort of organize the information. And I'm finding even with my pre-calc kids right now, one of the big things is where's your picture? Where do you have things labeled? Things like that. And just continue to work with them in just making sense of the problem before they even try to start making formulas. So, so some questions that are asked are, what's an equation for the perimeter of my garden? What is the general equation for the area of my garden? What are the system equations that relates to my garden? So at this point, this is another really powerful situation where we have a perimeter equation and an area equation. So all of a sudden we've got these three variables moving around, and how do I actually create a function that would help me answer some of the questions about the garden? And so really important part right here, and that's where they're introduced, but connecting it with the systems of equations.
And this, our garden problem is famous because Lynn loves her garden.
I do love my garden.
She has a beautiful garden. So when we're trying to say, what kind of scenario should we have? And, what this farm animals, this, so the scenario can be changed depending on your culture, your students, the teachers, so that it's a little more personal. But that's why we have a garden, because we all know Lynn loves her garden.
And so, Jim, I would agree with you, too, that many students think that a picture is a problem-solving strategy that you leave in middle school and never use again. And they don't realize that as you move along into more complex math, how important it is to simply draw a sketch. I tell kids, if you watch me solve problems, I'm constantly drawing pictures and labeling and all of those kinds of things, because it's really a very powerful strategy for organizing information. So with these problems, we can kind of reinforce this over and over again at different levels.
And then the next extension at this one is, what would happen to your equation if you only needed to fence 3 sides of the garden? So this is getting up to where you're fencing against a barn, against the river, and now it's just 3 sides and what's going to be different. So it's the same but different. So pretty similar to the prior. Again, the scenario is the same. Draw the picture, come up with the equation, but in this they're coming up with the equation and they're not being asked the scaffolding pieces of what's the equation for the perimeter first, and then to put the pieces together.
Bring it down. Yeah. I want to bring it down because I want to see the questions.
Yeah. Oh, sorry.
So that they can actually
read the question
again. Yeah. So, and then again, we're asking a lot of the same questions, and in this case, as Kim was saying, there's a lot less scaffolding, but we would hope that at the pre-calculus level, we wouldn't need to do much of that. But at this point, they're like, oh, yeah. And so they're feeling pretty smart and all of that kind of stuff. And then we give them this next problem.
So now we've changed the scenario a little bit. And we've changed the numbers, we gave them the picture, but they still have to understand what's going on in the picture and then come up with the dimensions in order to have the maximum area. So there's really no scaffolding. They've got to think about the whole problem on their own. So it takes them to a little different level.
And so there's some things where, they have to, they can only afford 600 feet of railroad ties. So kids need to make the connection that we're talking about the length around things along with the piece that goes through the middle of the peas and carrots. Also, we've got an area situation now that's not just length times width, but the peas need twice as much area as the carrots. So kids have to kind of start juggling a lot of different ideas together and learning how to kind of approach a more complex problem. And again, notice very little to no scaffolding whatsoever on this one.
Yeah. And then a common extension to this is to give a set amount of money, and the fencing inside the garden is a different price than the fencing around the garden, and kind of adding that next level of understanding for the students. Then we went to this next one, and now we have two different gardens, a circular PTP, which Lynn taught me about PTPs, and a square foot garden for carrots. So our peas will be in one and the carrots will be in the other. We have the 600 feet of fencing, but we have to take that set amount of fencing and cut it into two parts so that we can enclose each of the garden plots. So got to come up with their area as a function of the length, domains, what dimensions I want to maximize, circle, maximize the area in my circle and in the square so I have the maximum growing area. And things that come up is, can I put all the fence and just grow peas? Can I just grow carrots? And good discussion pieces and that. And then extending again a little bit, how much dirt am I going to need? So we want a constant width or constant depth, how much dirt will I need?
So that's kind of leading into a calculus level. Although the one before that is a classic, you have a wire, cut it into two pieces with a circle and a square. Where should you cut it, etc. So, all right, so our last bit. Thank you for being patient with us.
So our take home with this for you is, with your department, can you find a powerful problem, a rich task, an advanced level diagram or graph that could span all the grade levels within your department? Come up with what are the skills that are identified at each level that you would say at this level 1, I expect students to have XYZ technology skills. I expect them to have these math skills, these concepts. How did those change as they progress through the courses and improve? And the goal, of course, is that we really get that deep understanding and mastery so that we're not feeling like every year we're reteaching the same thing that we'd like to say, but didn't you already learn this?
And what's important, too, is we sometimes have people who are very zealous about getting the kids to learn so much, and sometimes it helps to say they don't need to know that yet. What they need to know is this breadth of ways of approaching a problem, not just keep adding new things. And so it allows for all of that discussion. And then in course breakout groups in your department, you can use that single prompt for different groups to brainstorm ideas for the grade band, connect to past lessons and strategies, anticipate potential difficulties, and then decide how could I ask questions that would allow kids to either wrestle with those difficulties, encounter them head on, or give them some scaffolding to be able to go with those difficulties. And then finally, develop questions that are geared to that course level. So those are just some ideas about how you could just take one simple graph and make it into this wonderful activity from year to year that help kids grow and mature mathematically with something that's familiar and also gives them an idea to see the richness of mathematics. That one time that they've seen something doesn't mean that they've explored everything that they could about that situation.
So what are some questions, we want to give a little bit of time, are there some questions that you have that you'd like to ask us at this time before Michael wraps things up or brings anything else in? This is your time. So, on your computer,
yep,
I can't see it.
In fact, one thing that we're going to do tomorrow in our department, we just got an invitation for our department that we are going to discuss how we talk about financial math or math from, well, the new financial math requirement, but how that might look in a course on its own, but also then how might it look at different levels throughout Algebra 1 through a pre-calculus level. So we're kind of trying to strategize a little bit about that idea. I'm kind of excited to see what we might
come up with.
Yeah. So what are some other topics? I know that in statistics, I teach AP Stats, and I think one AP Stats kind of backwards creating question is the idea of taking an exponential function using, say, M&Ms and counting the decay or growth by throwing M&Ms, counting how many, say you start with 60, throw them out, how many of the M&Ms have M's on them, you count those, and so for that one roll you might have 50. And then you take those 50 and you re-throw them out and count how many M&Ms are showing up, and it might go down to, I don't know, 32 or something. And so by doing that, kids can do a variety of things statistically at different levels and looking at the exponential decay function. But eventually in stats, what we end up doing is talking about how do we take a curve like that we get data and linearize it. And so there's a whole lot of different things about logs in earlier grades and how we can attach the idea of logs to other things. So I see a question. Thank you. I hope it does have some good ramifications for your department. That's Jim. I hope that you're able to use some of those ideas. Yeah, we found it to be very powerful.
So any other participants have questions, input, ideas, extensions, topics?
We don't want dead air though, so that's the problem.
What's that?
Statistics, probability of drawing a particular color from a bag. Yes, Marsh does have that. And I think taking one of the classic maybe inference problems from AP Stats and then working backwards into the data collection aspect of it or the inference without getting into the technical parts at an AP Stats level. There's lots of things that kids can do. And I noticed, there's some really good problems dealing with exponential functions and logarithms and then tying that into linear functions. I'd have to kind of think about it a little bit more. I haven't looked at it lately, but there's probably some things that you can do that way.
And statistics was a big one. We noticed a number of years ago on our state exam that the students struggled the most with statistics. So we had a big department about how could we bring statistics in at every level and not just the one time and said, oh, that's good, you got it. And what would that look like if we're going to bring that statistics in multiple courses and at different levels so that it changes in the way that it looks. And we really found our students' test scores in the statistics area increased once we started having more of these conversations and bringing in the stats at a variety of levels and not just one time.
So Katie brings up that she does humans versus zombies game with her students, and then they plot the data, and then you might be able to extend that. I'd be curious, in what way would you extend that, would you do a statistical distribution of what the different students came up with? Katie, I'm curious of what you were thinking on that one.
She's probably typing. She's typing.
I'd like to believe that. I don't know, maybe not.
Okay. Anything
So-
else? Because I can't see your screen.
Nope, I'm reading them as they're coming up.
Wow.
So, this has been really fun, don't you
regression,
think?
statistical regression, Katie said.
Oh, yeah. Statistical regression, that would be great. And even taking it, looking at what would a linear function look like with it, and then what other kinds of functions might fit. And having kids fit a curve to maybe picking a best fit line versus a regression line first to review, finding a quadratic function, a power function, things like that could be really good at different levels. Okay, well, I'm trying to think of, can you think of anything else that maybe we should add?
No, the only thing I would say is if you want, sometimes trying to start something big in a department can be a challenge.
Good.
So maybe the calc and the pre-calc talk together, or maybe algebra 1 and geometry talk together about what's a common problem that they both share, and just work at 2 levels to get started, because it can feel a little overwhelming to say, what am I going to do? And having that buy-in for everyone always sometimes doesn't always work initially until we start seeing the success of having some of these problems that are really powerful.
Another thing, too, I think that's important is not to feel like you have to do it for every single topic tomorrow. We have a real good colleague friend who's retired now, but she reminds us all the time that, pick 1 or 2 things for the year that you want to do. And so just picking 1 problem per semester and trying to flesh that out with your group might be a great way to go. You can't do this all in 1 year. I'm just going to tell you right now that we've done it for many, many years. So I'm noticing Rebecca.
She had a question I missed.
It says, I love the idea of showing my earlier years how what they're learning is going to grow, and showing my older students how crucial the foundations are for their concepts. And when kids can start making those connections and they start recognizing it, like, oh my gosh, we did this last year. Oh, this is how we can take it to that next level, becomes really powerful for them. It empowers them as learners.
Mm-hmm.
So.
Yep. Anything else? I think this is where Michael picks up.
But maybe.
But I don't know, because he's got to get that drawing done and
all those other things.
I know, all the other fun stuff, and I hope everyone learned at least one. I always say, if I learned one thing, I've learned a lot. I'm always growing and learning. See.
It looks like Michael is there, so I think you can stop sharing your screen.
I can. Yes, we could go back. I know, it's like the right place.
Thanks so much, Kim and Lynn.
There he goes.
There he goes. You want to stop sharing, yeah?
Oh, there I go. There. Okay. I know I'm going back to there's Michael. Okay.
Michael's going to do it.
Yeah. There it is.
Thanks so much.
Yeah.
There you go.
As we wrap things up tonight, we're excited to announce that the T-Cubed International Conference is coming to Dallas this coming March. It's a great place to connect with other fellow-minded educators. And right now there's still some early bird pricing available on our website, education.ti.com. So please feel free to visit our website to learn a little more about the T-Cubed International Conference. And tonight we're giving away to one lucky winner a registration for that T-Cubed conference. And tonight's lucky winner is Mary Jane Matlowski. So Mary Jane, congratulations. We'll be in touch over email in the next couple of days to give you a little more information. But you'll see Mary Jane as well as everyone else at the T-Cubed International Conference. Also available on our website, we currently are running the Extra Credit for Teachers contest. This is just a way that you can earn weekly entries for a chance to win some great prizes for your classroom for doing things that you're probably already doing, such as attending this webinar. So if you, again, visit our website, education.ti.com, you can learn a little more about the Extra Credit contest. But if you want the code for tonight to earn those entries, The code is not case sensitive, and I'm going to type in the chat window. It's Connect Math, all one word. Again, not case sensitive, and that's the code for the extra credit for Teachers Contest. To receive a certificate of attendance, go ahead and copy that link or click that link in the chat window. Also listed as a link for the documents that were used by Kim and Lynn tonight. And if you're watching this on demand, go ahead and copy that link into your favorite browser to receive your certificate. So thanks so much, Kim and Lynn, for everything you shared tonight. I already saw in the chat window some great praises. So thanks so much for everything.
Well,
thank you, Michael. We had a great time.
We enjoyed it. Oh my gosh, you think we were two Siamese twins here or something?
Well, thanks so much.
Thank you.
And,
yeah, great evening, everyone. And if it's late, good night. And thanks for joining us. It's been really wonderful.
I agree. Thanks so much for joining us, everyone. Hope to see you back online real soon. Have a great night.